This is section 10.2, confidence intervals for the difference between two means, paired samples. This is the analog to, or maybe you could say the continuation of, what we did last time where we looked at independent samples, two samples that had nothing to do with each other. Here the samples have everything to do with each other. So we're looking at another two-sample confidence interval. You'll see some of the methodology is similar, but some of it's different. And again, we're looking at a confidence interval for paired samples, which is samples whose observations can be, well, paired with each other on the individual level. And so again, we are looking for a confidence interval of the parameter mu1 minus mu2, just like before, but again, with paired samples. Now remember, last time we looked at independent samples, and the exam scores were measured. Right, remember we had those exam scores where like 35 students took an online exam, 35 students took a paper exam. They were separate, they were different people, they had nothing to do with each other. The exam scores were measured independently, making the samples, well, independent. Right? And because they were independent, we used a large standard error. And remember, the standard error formula was this guy. Right, that guy. So it's kind of a bigger, and it's not a huge number, but it requires both standard deviations, you're adding them together, etc., right? It's kind of bigger than what we're used to seeing. But instead, if we could have somehow paired these students, if we could have somehow paired student one with, the first student who took an online test with the first student who took a paper test, the second online student with the second paper student, etc., we could have had nicer numbers. And we would have had what's called paired data. Each data point would have been, well, paired with another, right? And we call paired data, well, matched pairs, right? Because we're not just arbitrarily pairing the data, we're pairing 2 points that are really matched with each other. It makes sense to pair these. We'll look at an example in a sec. Why wouldn't it have made any sense to do that in example 1? Well, if the same 35 people took both the online and paper exams, then we could have paired them. We could have paired their exam scores, but their second exam scores likely would have been higher. Right, regardless of whether they took paper first or online first, whatever they took second, they probably would have done better. So this would not be a good thing to, if we really wanted to see how students did on online versus paper exams, we shouldn't prep them, by having them take one exam and then taking it again with a different medium. So that we did need to use independent samples for. But let's look at this example, a situation where we have 5 subjects, before they've been given a medication and then after they've been given a medication. Here it makes sense to pair their blood pressure before the medication with their blood pressure after the medication, right? So we take the patient's blood pressure before, give them medication, take their blood pressure after. It makes sense to pair them this way, etc. Okay, so if we construct a 98% confidence interval for the mean reduction in blood pressure, right? So the mean difference between before and after. So you could think of that as mean before minus the mean after, right? Because that measures the difference, right? That's sort of what we're doing, okay? So what we're going to do is we're going to open up Excel. And we've already got the numbers right here. Oh. Actually, I guess I don't need the... Okay, I'll just go ahead here. And I will go over to paired T. Okay. In case we have these 5 data points. Let's get rid of those guys. Get rid of these guys. Whoop. And there we go. And so you see what happened in this column right here. We have the difference, right? Sample 1 minus sample 2. And really, we're taking the stats on this column, okay? So if we decide that, hey, we want a 98% confidence interval, well, those are our numbers. Let's do this guy right here. Maybe I'll just paste it right here. And maybe I'll include it here. Oh. All right, and anyway, what we're gonna say is, maybe I'll move this guy over here, and we'll just say 98% confidence interval is, what would you say it is? 19.1663 to 43.6, 337. There it is. Okay, so based on the confidence interval, is it reasonable to believe that the mean reduction may be 50 millimeters per mercury? No, because 50 is outside our confidence interval. Okay. Now, what we did was, you might say, well, isn't this the same as what we did last time? Yes, except our standard error is smaller than it would have been for a comparable independent sample, right? Because our samples are pairs, we can define statistics based on D, right, which is going to equal x1 minus x2, right? So what we're really interested in is finding x bar of D, the sample mean of D, which again equals x1 minus x2. We're finding T alpha over 2, which is, as always, the critical value of our confidence interval. And then we find SD, which is the standard deviation of d, which again is x1 minus x2. Then find the standard error, SE equals SD over root n. Now remember, there's only one n in this case because everything is paired. Sample 1 and sample 2 have the same n. So then we're going to compute the confidence interval. Well, maybe you can see what's coming here. It's going to be xd minus the margin of error to x bar d plus the margin of error, which of course is x bar d minus our critical value times our standard error, x bar d plus our critical value times our standard error. And that, of course, is the same as this guy once more, times sigma d over root n to this guy plus this guy times sigma d over root n. Okay, so there we go. And I also just want to make the point, note that matched pairs is really a one sample confidence interval on, I guess I should say on D, which again is x1 minus x2. Right, and what I mean by that is if we just took, right, if we go back here and let's see if it lets us copy this data, and we go to one sample T. Oh, it's not going to let us do it. Okay. If we just remember the numbers. 25, 32, 39. 25, 32, 39. And then we had 23, 38. Right? Look at these values. See how it's the same thing? Let me just keep that there. It's the same exact thing that it was before. So if you want, you could do that. Right, but you could also just enter each pair of data in. Right, it's probably easier that way. But just pointing out. Maybe I'll just do. Compare that with that. It's the same thing. Okay. And know that the standard error in example 1 was only, well, let's see what it was, 3.265 instead of, well, suppose we had done it with independent samples. Well, that would have been, yeah, and actually let's just see how we got that, right? We got it as 7.3007 over the square root of 5, right? As opposed to, we could have done the square root of, what would this have been? This would have been, well, I don't even know. Let's go ahead and copy paste our data into the 2 sample T. So ready, let's do this. This guy into here. And then here. And look what our standard error is in this case. It's 5.31 because standard error number 1 is 9.26. We would square that, divide by root 5, plus, and then what was the other standard error? 7.43 over root 5. And that gave us, what was that? 5.31. You see how See how this is just superior to this? Like, it's lower, and lower is better. It means we have a shorter confidence interval with the same amount of confidence. Right? And of course, we're always using Excel to quickly construct our interval, okay? So you can pause the video and read this, but we're gonna do the same thing as before, right? Create a 90% confidence interval, based on this data. And then we'll copy this guy. And we want a 90% confidence interval, so we just put in 0.9. And we get our answer. All right, there you go. Right, so 90% confidence interval. There you go. And if a physician claims the mean reduction in cholesterol is more than 80 milligrams, per deciliter, does the confidence interval contradict the claim? No, sort of a double negative. The 90% confidence interval does not contradict the claim. Why? Because 80 is within confidence interval. So 80 is a reasonable estimate for the mean difference. Okay? Now, just quickly, we need to make clear what assumptions that we're making for these paired intervals. Well, first of all, we have to have two samples that are paired, okay? And of course, they need to be random. And of course, our sample size needs to be large, or our differences need to come from a normally distributed population. Okay, let's do one more example. All right, you can pause and read that. Construct a 95% confidence interval. Well, we're just gonna go ahead and copy paste our data. There we go. So again, this is the difference data, right? This is the difference for each pair that we have. And I think they were looking for a 95% confidence interval. They were. And so this is our stuff. So let's just write our answers down, paste it over here. Our 95% confidence interval is 1.0071 to 3.2373. Okay. B, is it reasonable to believe that the mean mileage may be the same? Well, no, it's not, because mu1, I should say, yeah, I'll say mu1 minus mu2 equals 0 is outside or not in our confidence interval. So it is not reasonable to think that the difference could be a value outside our confidence interval. And that's what we've got.